Hi, everyone. My name is Aravind Sriram. I'm an architect at Adobe. And today I'm going to be talking about how we build a graph database that can serve millions of queries per second. Right? A little bit about me. I've been in the industry for about 15 years. Started out in the natural language processing domain, but somehow gravitated to the ad tech industry. My areas of expertise include building high throughput, low latency Java applications like real-time ad servers and bidding servers, and also working on distributed databases like Cosmos DB, Aerospike, and others. I've also worked on data pipelines like Spark Streaming, Spark, and Flink. And at Adobe, my key contributions include architecting the identity graph system, and I'm also responsible for sort of introducing Aerospike and Foundation DB at Adobe. So before I get into the talk, I want to spend a second talking about Adobe and the product, where this fits in. Can I have a show of hands? How many people here have heard of Photoshop? Adobe Photoshop. OK, very popular. Great. So Photoshop falls under the Creative Cloud division of Adobe. So this is a creative suite of products where you have Premiere Pro, Illustrator, Photoshop. And the goal there is to unlock creative productivity, right? PDFs, I bet everyone in this room know and understand PDFs. So PDFs fall into the document cloud business, and the focus there is document productivity. There is a third business unit that is emerging, and it's the least known of the business units in Adobe. Has anyone heard of Experience Cloud or Experience Platform? OK, that's what I thought. So Experience Cloud is the third business unit in Adobe. Their focus is on building marketing software, right, where we power retailers like Macy's, Verizon, and a lot of the Fortune 100 companies to run various marketing campaigns, right? So it's a combination of customer data platform and a suite of marketing products. That's what fits under the Experience Cloud umbrella. So one of the key problems that you need to solve for the Experience Cloud business is personalization at scale. So customers don't just want to buy products. They want to engage with brands in a way that feels authentic, personal, and human, right? And you need sort of marketing software that will allow brands like Macy's to connect with millions of people, but in a very personal, one-on-one way. So the key challenge there is how are you going to solve for personalization at scale? And you do that by unifying data. So typically, customer data comes in from a variety of systems, and you have various silos. And you need a system that can unify data and build real-time customer profiles. And once you have this unified view of the customer, you can now have an omni-channel journey. You can sort of target a customer across multiple touch points and surfaces like retail or apps or websites, right? So that's personalization at scale. And one of the key sort of foundational technology that you need to do that is called identity graphs, right? And what is an identity graph? It's simply a graph of various identifiers that represent a single consumer, right? So in this example, you see sort of different IDs like CRM IDs, device IDs, anonymous cookie IDs, and so on and so forth, right? So a graph of all of those identifiers is called an identity graph, and that's what enables like customer data platforms or marketing software to build unified customer profiles. And that is really essential for the personalization at scale story, right? So one of the teams that I'm responsible for at Experience Platform is the identity service. And there are three key facets of this service or team. There's identity collection, and it happens at really large scale. We collect about 26 billion records or process about 26 billion records every day. And we use that to build about 50 graphs that have 50+ billion identities. And we have APIs that can operate at millions of queries per second, right? So it's a really high-scale system, and that's one of the interesting aspects of it. The other interesting aspect is it deals with graphs. OK, so when you think of graph data structures, immediately you think of graph databases. And we did look at a whole bunch of graph databases to see if they would natively solve the problem. Unfortunately, none of the existing graph databases met the kind of scale requirements that this particular application required. And so we set out to build sort of our own custom solution. The way that we went about it is we started with a very scalable key value store as a base layer, and then we tried to build a layer on top of that that will provide graph abstractions, right? And originally, the 1.0 version of this was built on Cosmos DB on the Azure cloud. So the Cosmos DB was the distributed KV layer, and then we built the graph layer on top of that, right? So I have some content here kind of talking about how you can store graphs in a key value store. How do you kind of think about that, right? So there's like different ways that you can think about storing graphs in a key value store. One way is you can sort of look at, in this example, you have two graphs, and you can build an adjacency list for those graphs. And you can build a table structure that says for each node, this is my adjacency list, right? And I'm referring to this as graph partitioning by node, where every node is its record and a row in a table, right? It's a pretty simple but effective sort of way to model the graph. Some of the pros is that you get a very simple physical data layout. It's very scalable. And you can support all kinds of graphs, social graphs or identity graphs, right? Some of the other considerations is if you needed to query a component, for instance, the ABC or the XYZ components, you would have to do an O of n operation and then do that many number of lookups to materialize the graph. And if you had any requirements around having to look at that component every time you do some ingestion, and in the case of identity graphs, we have that. Or if you have to produce a change log that states this is the view of the graph before my ingestion and this is the view after the ingestion, you do require you need to materialize the graph, and that becomes an O of n operation and affects your performance. The other aspect is if you are modifying multiple rows, you need some sort of transaction support for correctness, right? There is an alternate way to also partition the graphs, which I'm calling as partitioning by connected component. So effectively here, the strategy is you serialize each of the components that you have, and you store them in a table, right? So there is a graph table where you can serialize the various graphs that you have, and you associate sort of an identifier for that component or that graph, and you store that in a separate table. And then you build an index over that where each of the node labels will point to the graph identifier, right? So you end up with a two-table sort of a structure of an index table and a graph table, right? Which works for certain applications, and it does work for identity graphs. And if you look at what are the pros of this sort of a structure, the lookup is a O of n operation. You do two lookups, and then you can get the whole component in one shot. You also get slightly better data compression because of repeated metadata that you tend to see in edges of the same graph. And if you have requirements around having to associate like a stable identifier with a component or a graph, it's much easier to do that in an online fashion in this structure. There are some other considerations in the sense that you do need an additional table, and it's not really the kind of partitioning that is suited for storing larger graphs. It works when you have a large number of small graphs, right? And you also require transaction support because you want to make sure that your index updates and your data updates are sort of done with transaction isolation, right? And you can also end up with a hybrid model, which is neither a node partitioning or a connected component partitioning. You can sort of have an in-between model where, depending on the kind of data, you make a choice to either do a node partitioning or a connected component partitioning, right? So what we did is we built a graph layer for key value stores that used the connected component partitioning approach, and it's kind of pluggable, so you can also plug in a node-based partitioning if required, right? So it's a layer that is written in Java. It provides a rich data model using Google Guava and Java generics. And it supports generating change logs. Every time you change the graphs, you can get like change logs of what was the previous view and the view afterwards. And it also allows for a user-provided serialization, compression, and encryption. So it provides like a module pattern where user can bring in their compression or encryption, and it allows you to plug into that, right? And from a layering perspective, at the highest level, you have the APIs. So that's where you would issue your REST request. And then there is a graph access and storage manager layer, which sort of takes on the encryption, compression, and serialization aspects. And there is a transactional KV client abstraction, which lets you basically connect to any key value store that supports ACID transactions, right? So, and we use this database called FoundationDB, but it's simple. As long as there is a database that supports ACID transactions, it's easier to switch to any database. So with that, I want to spend a little bit of time talking about FoundationDB. This is the database that we use at Adobe for managing identity graphs. It's a distributed, scalable, fault-tolerant, ordered key-value store. It's open sourced by Apple and Snowflake, the two main contributors to that project. It supports ACID transactions at the strict serializability level, the highest database isolation level. There's multiple configurations for high availability in terms of fault tolerance. You can have multi-AZ or multi-region setups, and you can choose to have 3 copies of the data all the way up to 6 copies of the data. It is a sort of a foundational layer. It doesn't offer a lot of things like schemas or indexes. The expectation is you manage schemas and you build your own indexes, or you rely on some higher layer like the record layer, which provides these functionalities. Out of the box, it has a byte array key and a byte array value, and that's the API that you need to work with. Another interesting thing about FoundationDB is that it is, before writing the database, they built a very comprehensive simulation framework, and every aspect of the database correctness is validated through that simulation framework, right, to the point where an interesting comment that was made by the person who runs the Jepsen test is that he said he didn't bother running Jepsen because FoundationDB simulation framework is way more sophisticated than Jepsen itself. So from a correctness perspective, there's a very strong story there, right? And it's open source, and like I said, Apple and Snowflake are the two key players, contributors for the project. So at Adobe, we run about 20 production clusters in various regions across the globe in both AWS and Azure clouds. Each cluster is 45 VMs or 360 vCPUs, and we run them across 3 availability zones. And each cluster can store about 4 terabytes of actual data. This is at a storage utilization of 50%. So, obviously you can go more, but our target is 50%. And we go with a very safe configuration, which is called multi-region with 1 satellite triple. What ends up is we have 6 copies of data that's spread across 2 availability zones. And then we have 4 copies of the transaction logs that are spread across 2 availability zones. So we get really good fault tolerance capabilities from this setup. We can lose any one AZ, and there wouldn't really be an issue. It would behind the scenes cut over to a different AZ, and you wouldn't have any downtime per se in this scenario. We could also lose any 4 machines. Any 4 machines of the cluster can go down simultaneously, and nothing would happen. If we have staggered failures, we can tolerate like a lot more failures. The only essential aspect is there is a set of processes called coordinators, and its effect is essential to maintain a quorum of those coordinators. So that's one thing to sort of keep in mind, right? So we've run like, so how did we land at FoundationDB? We actually looked at a few databases. This was 5 years ago. We looked at CockroachDB, TiDB, and FoundationDB. This was 5 years ago, and we wrote a benchmarking automation suite to automatically evaluate all these databases. Given a set of parameters, you could sort of trigger the tool and then come back in a couple of hours, and then it will have a nice CSV report of the results for the various experiments that you've defined. So it's open source. You can go check it out. It's at the Adobe GitHub page. And it runs in Azure Cloud, but we also have a contribution from AWS to run it in AWS Cloud, which is not yet in the open source repo, but eventually it will get there. And it supports metrics integration with Prometheus and Grafana. And like I said, these are the 3 databases that were supported, right? And After that evaluation, we pick Foundation DB, and that's what powers the identity graph database. And then we can add new databases into this framework and sort of keep evaluating to see what the performance characteristics look like. So from a read perspective, we get really good performance from FDB. That's one of the main reasons that we picked FDB. So this chart is showing you as you increase the amount of load generating threads from a single 45-node cluster running in a multi-region configuration with 6 copies of data across 3 AZs, what performance you can get. So we are observing about 4.2 million reads per second, 2 kilobyte records, right? So that's the number that we get for each of the clusters, and we run about 20 of these clusters globally.
What is the size of it?
Sorry?
What is the size of it?
So you're asking what is the size of the database?
No, the read operation.
It's 2 kilobyte documents, 2 KB, yes. And the database itself, like I said, we load about 4 terabytes of data to get a 50%-ish storage utilization, and then we run the benchmark to make sure that it is a representative benchmark. Yeah. I also have some numbers for basically update and writes. We get about 150,000 operations per second on that 45-node cluster in the multi-region setup, and you get a different set of numbers for the 3 data hall because you only have 3 copies of the data in that setup, and so you get different fault tolerance trade-offs and performance trade-offs. Okay, so now that we have this transactional store, not all of our workloads are transactional. We have analytical workloads as well. So how do we run analytical workloads on a transactional store, right? So the way that we went about it is we implemented a changelog feature on top of Foundation DB. What we did in our graph layer is for every session, we maintain the keys that were read and the keys that are being written to the database layer, and then we are able to build a changelog and serialize the changelog and write it as part of the same transaction. So every session that we start, we are keeping track of all the values that we read and then we wrote, and we use this table to create a changelog, and we write that changelog as part of the same transaction. So it's an atomic. If the mutation happened, you have a changelog, and there is no possibility that if a mutation happens and there is no changelog, right? So, which is a really good property. So then we have a system where we siphon off these changelogs and we archive them into Delta Lake. So we get like basically a Delta table that has all the changes for a given database. And then we have another process that takes these changelogs and aggregates them, and then it merges them into another master data set in Delta Lake. So effectively, we have a one-way replication happening from the database using the changelogs into data lake, and it is eventually consistent in the sense it takes about 10 minutes for the mutations to flow from the transactional store into the analytical store. But it's a consistent snapshot. If the database goes down with the 10-minute data loss, we can actually restore from data lake, and that's actually possible. In reality, the latency is much lower in the low minutes, but 10 minutes is sort of what we advertise as an SLT. Okay, so what are some lessons learned through this entire journey, right? So one key aspect, if you're going to be deploying distributed databases in, say, Azure Cloud or AWS Cloud, is to look at the choice of disk. Are you going to go with managed disk, or are you going to go with local storage, right? And they offer different trade-offs. One key trade-off, the obvious one, is performance. Local storage offers extremely high performance. For instance, if you take an EBS disk, you're looking at a few hundred megabytes of bandwidth. A local storage disk, you're looking at a few thousand megabytes per second of bandwidth. So there's like a huge, and the newer ones, it's almost 5,000 megabytes per second. So there's a huge difference in latency and bandwidth that you can get from local disk versus managed disk. The other aspect is whether you're OK with aggregated or disaggregated storage. What I mean by that is aggregated storage is where storage is tied to compute. When you go with local disk, the local disk are part of the actual node itself, and therefore, if you want to scale for storage, you have to scale the nodes out. So that's aggregated storage. Disaggregated storage is where you attach like your EBS, where you can scale the storage aspect separately from compute, right? So that kind of plays into your design choice. If you go with local disk, it's aggregated storage. If you go with EBS type disk, you're going to have disaggregated storage designs. Another key aspect is data durability. Local disks survive VM restarts, but they don't survive host maintenance. So what that means is, in terms of a durability, if there is some host maintenance going on, you will lose the data. And if you turn off the VM, you will lose the data. So as opposed to if you look at managed disk, they offer various levels of redundancies. You have zone redundant, local redundant, globally redundant, and there's like all sorts of flavors of redundancy that you can get. You can take the disk and attach it to a different node. So in terms of durability, it's a very strong story for managed disk. Encryption is another key item. When you have managed disk, there's very sophisticated encryption capabilities like customer managed keys and so on and so forth, which you do not get at local disk. Local disk simply give you encryption at rest. And so if that is a key consideration for your application, you should think about that choice. Managed disk offer features like disk snapshot, so you can take a snapshot of the whole database in just a few seconds, and that's a powerful feature. In fact, FTB, there is some support for snapshotting where you can kind of pause the whole cluster for a second, take a snapshot, and that's. Otherwise, you'll be expending a lot of compute resources to take the data out to do a backup. A snapshot is a very efficient way to get a copy of the whole cluster. And the restore process also works extremely fast. You don't have to pump the data in. You just pre-warm and you bring it up, right? So local disk, you would have to rely on file system features to do it. It's not straightforward. Managed disk, these are all built-in features on both AWS and Azure. The last aspect is availability in public clouds. In AWS, you have the i3 and i3en instance types. They are the only instance types that give you local disk with different densities for the data. In Azure, it's the L series of VMs that give you the local disk. So you're kind of limited in the kind of VMs that you can use when you go with local disk. As opposed to managed disk, you're free to pick your own VMs and attach whatever disk you want. So there's more flexibility there, right? So this is something to consider when you're building your clusters. What is the right choice for you? Are you going to go with managed disk or local disk? In our instance, local disk was the right set of trade-offs, so that's what we went with. Another aspect is to look at your compute. Depending on the kind of distributed database you're running, you could have different types of sort of roles, and therefore you can build a cluster that is most suited to that. In our case, we had two classes of nodes, stateful and stateless nodes. Stateful nodes were more expensive because they had the local disk, and stateless nodes were compute only. So that is a way to kind of trade off cost. Another consideration is, are you going to be multi-region or multi-AZ? Single AZ is not something we would ever recommend, but the choice really is to make between multi-AZ and multi-region. There are trade-offs with respect to fault tolerance, performance, and cost. There is also cost when you go across AZs, although that's a smaller amount compared to going across regions. And in terms of complexity of your deployment, there is some variability there. The last aspect is networking. For FTB, there was a requirement that all the nodes, all the client machines need to be able to directly talk to each of the nodes of the cluster, which is a unique challenge in various corporate environments. But there are ways to work around that using VNet peering or transit gateway. Both AWS and Azure has various methods through which you can kind of tunnel through different networks to achieve that. In terms of your application design, think of your keys. Are they random? Are they sequential? That's going to have a huge impact on your performance. If you have repeated prefixes, think about trying to sort of condense them by mapping them to a short prefix and then using the shorter prefix in your keys. That will give you a lot of performance and cost savings. If you have duplicate data, think of how you can manage hotspots and conflicts. That's another aspect that reduces your application performance or your database performance. Consider using batching. So one of the things that we do is every time we do a write, we use one transaction to process like 10 or some number of records. So that allows us, that transaction reuse allows us to hit higher performance numbers. On the read path, similarly, we reuse a single transaction and service multiple API requests using the same transaction, and that allows us to sort of increase the performance that you can actually achieve. Changelog is like a very key feature for us. It serves multiple purposes. The first one that I kind of covered is being able to replicate the data from our transactional store to the analytical store, the data lake. Changelog is what powers that. It also acts in a sense as a continuous backup. And we are actually rolling out features where we can now migrate data between clusters in a live fashion without downtime using this changelog. So in some sense, we spin up another cluster and we start replicating all the data from cluster A to cluster B to the point where they're very close. And then we do a cutover to reduce the amount of unavailability for the client while migration is happening, right? So changelog is a very powerful feature. So think about how you can use changelog in your sort of application. So if you're going to do benchmarking, some things to be mindful about, like model the load in terms of the key and the value and the distribution of the size for the values. Think about what your request distribution is going to be like. Is it a uniform distribution? Is it a Zipfian? Is it a log normal in terms of users arriving on your site? So that's important. Make sure to bake in things around conflicting transactions in your workload, so you get to exercise that when you do the benchmarks. Look at batching. Batching is a way to improve performance, so include that in your benchmarking. And always target 50% storage utilization, because if you run a benchmark with only 5% of the disk full, it may not be reflective of what happens in production. In a lot of databases, it's important to pre-partition. When you do a cold start, the performance may not reflect what actually happens in a real-life production scenario. So think of pre-partitioning. And the number of clients that connect to the database has an impact on the performance and the availability. So definitely include that as a dimension in your benchmarking, right? And then the last point is without automation, it's impossible to do any kind of reliable benchmarking. So you need to have automation and be able to repeat these benchmarking experiments, right? With that, I end my talk. Thank you for your time and attention.